record. And now we're beginning. Please, Marie.
Thanks for the introduction, and thanks for inviting me to talk here. So I'm afraid some of you may have already heard most of that, but so it's about the three variable property for linearly ordered structures. So basically the general question we're interested in is this one. So how many variables do we need to be able to express every first order formula? So in general, we may need unboundedly many variables. So for instance, if you want to say there are at least n distinct elements in our model, we can write this like this in first order logic. So I always assume that I have the equality at least. But we cannot write an equivalent formula with less than 4 variables in this case. The situation is a bit different when we look at a particular class of structures. So for instance, in verification, we are often interested in particular class of models. So for instance, if we have a linear order in every structure, then the formula above can be easily written with only 2 variables. So we just have to find 4 distinct elements going from left to right. So we say there is some x, and then I can find a y later on, and then I can forget about the first x, and I can reuse the variable to say there is a third element later on, and so on. So what's important to note is that even if we have only 2 variable names, x and y, we can reuse them as many times as we want, and we can nest quantifications and so on. So we can actually say quite a lot, even with just 2 variables in this case. Or so in general, for the class of linear order, so if you have just one linear order and possibly monadic predicates, the 3 variable fragments of first order logic, so FO3, is as expressive as the full first order logic. So we also say that linear orders have the k variable property. So the obvious question is, why do we even care about the number of variables we are using in our formulas? So one first possible answer is that the number of variables a formula has is very important parameter in terms of complexity. So bounded variable, the complexity of different decision problems for bounded variable fragments, such as FO2 and so on, have been extensively studied. Bounded variable logics also play an important part of in descriptive complexity for this reason. So descriptive complexity tries to describe complexity classes in terms of logical definability. So in this context, the number of variables or the depth of a formula and so on are counterparts to the parameters like the time or the space Turing machine use. So in descriptive complexity, it's more fixed point logics and so on that are used, but still, this is an example of how looking at bounded variable logics can be important. So another domain where bounded variable logics have been extensively studied is temporal logics. So many temporal logics, such as LTL and so on, can be embedded into fragments with first order logic, which uses a bounded number of variables. And there are also interesting connections in terms of expressive completeness and so on. So for instance, just to illustrate how this can interact. So Gabi proved that in a given class of structures, it's equivalent to have the existence of a temporal logic given by a finite set of temporal connectives, where we assume that the semantics of every temporal connective is given in first order logic. And okay, so this is equivalent to so this the existence of such a logic is equivalent to having a k such that every first order sentence can be rewritten into one which uses at most k variables. So there are similarities, and there are also a lot of subtleties, different depending on the notions we consider. So, okay, so let's go back to the example I gave you in the beginning of linear orders. So I told you that linear orders have the 3 variable properties. So there are several ways to look at this. So there are two different techniques to prove expressive equivalence results such as this. So the first one is to go through temporal logic. So as I mentioned, there are tight connections. So for instance, we can derive the equivalence of first order logic and its 3 variable fragments over complete linear orders from Comp theorem, which says that first order logic is the same as in expressive power as LTL. So LTL can be easily embedded into FO3, which means that FO can also be translated into FO3. So this has been extended by Stavy to arbitrary linear orders. And I mean, this has also been applied to other types of structures beyond linear orders. So the second classical approach is to use Ehrenfeld games with a bounded number of pebbles, which corresponds to the bounded number of variables. So the result for linear orders and others has been proven in this way by Immermann and Kozen. And yeah, the idea is to find links between strategy with k pebbles and strategy with an unbounded number of pebbles. So I should mention that there is, in fact, some subtleties in that. So technically speaking, the two approaches do not prove the same results. So if we talk about temporal logic, we are only speaking about formulas with 0 or 1 free variable. So we are proving that every formula with up to 1 free variable can be translated into 1 in FO3. Whereas with Ehrenfeld games, we can talk about formulas with up to k free variables. So the approach I will take here is a bit similar to the first one, but a bit different because I will still be able to speak about formula with many free variables and so on. Right, so that's maybe the best known example of a k variable property. So linear orders have the 3 variable property. So now the question is, okay, so this applies to models where we have just this linear order and nothing else. And one natural question is, okay, what happens if we want to consider richer structures where we have possibly some other binary relations? And unfortunately, so if we just add other relations without assuming anything, then we lose the k variable property. Okay, so even if we have just one additional binary relation, so one linear order on the top of that one binary relation, so essentially we have totally ordered graphs, then the bounded variable hierarchy is strict. Now, there are also positive examples still, so there's still things to be said. One of them is the real numbers with the +1 relation. So Antonopoulos, Hunter, Raza, and Worrell proved that we have this 3 variable property over this structure. And there are other examples, so such as Mazurkiewicz traces or MSC. So this go a bit beyond linear order, but there are still some similarities. MSCs I was working on with Paul and Benedict. Okay, so what I wanted to do is try to identify why what all these cases where we have 3 variable property have in common. So what are the features that are sufficient to ensure that we have the full expressive power of first order logic with only 3 variables? And the answer to that is monotonicity. So what's all these classes have in common is some sort of monotonicity condition on the binary relations. So more precisely, what I proved is that if we have a class of structures where we have one linear order some binary relation, which are interval preserving. So I will explain what this means, and any unary predicates you may like. Then the 3 variable fragment is equivalent to full first order logic. So interval preserving is a sort of monotonicity condition, as I mentioned. So basically, it's just what the name says. So a relation is interval preserving if the image of an interval is an interval and the pre-image of an interval is an interval. So it's slightly more subtle than that, because what I mean by the image of an interval is that so if I take some interval I and I look at all points we can reach from I, so it should be an interval if I look only at points which are in the image of the relation. Okay, so I look only at the points in orange, so the end of orange arrows. And for these points, the image is an interval. And then I have the same condition for the pre-image. So if I, yeah, so for instance, if I remove this relation, then this will no longer be interval preserving, because I would have this point in the image, which is in between 2 points in I, and it's not in the image of I, so it's no longer an interval. Right? So then we have the converse condition. So all elements which are sent into I should form an interval in the domain of the relation. So we look only at points from which, so these 3 points, and then this is an interval indeed. So I don't know, maybe this seems natural enough, maybe this seems a bit weird. So don't worry too much about this definition. So because in fact, most examples I will give of interval preserving relations are monotone functions. So monotone functions are a particular case of interval preserving relations, and this is mostly the kind of examples we will look into. So maybe I can just prove this to explain the definition a bit. So if we have monotone function, so and the corresponding relation R, so if I take an interval and then I take any point which is between 2 points I can reach from the interval, then since it's, if it's in the image of R, then it has an antecedent and it must be in the interval because it's monotone. So that's it. So it's very straightforward that monotone functions are interval preserving. And we have the same for the converse, of course. Okay, so that's one application of the result. So linear orders with non-decreasing or non-increasing functions have the 3 variable property. There's even one more, the most basic application, of course, is if we don't have binary relations at all, then they are all interval preserving if there are none. So the result also apply to all linear orders with or without gaps and so on. It also applies to the result I mentioned about the real numbers with the +1 relation. So +1 is obviously monotone, so this is fine. Then there are some indirect applications, like, let's say, so for instance, if we have still the real numbers, but now we add polynomial functions as relations. So polynomial function is not monotone, but it can be divided into a bounded number of monotone functions. So we can still apply our result in this case. Right, and then one last example of applications is message sequence charts. So an MSC is just a graph like this. So it represents an execution of a message passing system. So you have a finite set of processes, P, Q, and R. Every process executes a finite sequence of actions, which are ordered by some process order. Okay, so you have one linear order for every process. And then you have a message relation. So for instance, here process P sends a message to process Q, which is received there. And we could add other relations in the signature, but like the haven't before relation, but we can always define it from just these two relations. So obviously here we don't really have a linear order. So maybe it's not entirely clear why my result apply, but we'll still have a linear order on every process. And we only have a finite fixed number of processes. So it's essentially the same as having one linear order. We could always put them one after the other. Then we have this, I mean, artificially, but we have still one linear order. And we assume that the processes communicate through FIFO channels. So the messages are received in the same order as they are sent. So this means that all these extra relations are monotone. So we are exactly in the setting I described. This is an interval preserving structure. So we have the 3-variable property. Okay, so this, just to recap the examples I explained. So there's also Mazurkiewicz traces, which are also more of an indirect application. It's similar to MSC, so I won't go into too much detail. All right, so I hope I have convinced you that there are some interesting examples of interval preserving structures. Now, what I would like to convince you to know is that it's the right definition from a technical point of view. So why does this assumption help? So I told you that if you have no assumption on the binary relation, then the 3-variable property fails. So imagine you have a formula like this, a first order formula with three variables, and you want to find an equivalence formula which uses only 3 variables in total. So only, I mean, this means that you cannot have this bound variable y, essentially. So the formula says there is a y which is related to x1 through r1, to x2 through r2, and to x3 through r3. So in general, I mean, you just can't write it without having this extra variable. But if you assume that the 3 relations R1, R2, and R3 are all interval preserving, then you know that the image of R2 is an interval, the image of R3 is an interval, the image of R1 is an interval. And the formula just says, does there exist a y in the intersection of the 3 intervals? Okay, so is the intersection of the 3 intervals non-empty? But I mean, to test if the intersection of 3 intervals is non-empty, you can simply check if the pairwise intersections are non-empty. Okay, so we can say equivalently that the intersection of the orange and the blue interval is non-empty, of the orange and red interval is non-empty, and the blue and red. And here I've teased a bit because, as I said, what I mean by interval with interval preserving relation is interval in the image of the relation. So I need to add that the point y is in the intersection of all, in the image of all 3 relations. So now I have this conjunction where in every part of the formula, I use only 3 variables, x1, y, or x2, x1, y, and x3, and so on. So I can just rename y into the variable that I don't use in every conjunct. And then I have my formula in FO3. So, I mean, of course, it's just one basic example, but that's really essentially the reason why having the interval preserving relation makes everything works. Okay, so now let me get a bit more into the detail of how we can prove this. So the idea of the proof is to go through an intermediate language, which is this star-free propositional dynamic logic. So translate every first order formula into this logic and then into FO3. So propositional dynamic logic is some kind of modal logic, if you will. If you're not familiar with it, don't worry, I'm going to explain everything. So I would like to start with giving you a bunch of examples of star-free PDL formulas, just to give you an idea of what it looks like. Then I will go a bit more precisely into the syntax of the logic. And finally, I will be able to explain to you how these translations work. All right, so in star-free PDL, we don't have any explicit variables, so we just have formulas which are evaluated at given points in the structure. So for instance, we have all Boolean formulas. So hopefully this is false at the red marked positions and true at the green positions. You also have some modalities. So for instance, this diamond RQ means I can follow an edge in the R relation and reach a point where Q holds. Okay, so for instance, from this point, I can follow this edge and reach a point where I have a Q. Now, what's interesting about PDL is that you can also have more complex expressions within the diamond modalities. So for instance, you can concatenate relations, you can take the converse of a relation. So for instance, this formula says I can go to the right, then I take an R edge backwards, and then I reach a position where I have Q. Okay, so for instance, from all those points, I can go to the right up to here. I can take this edge backwards, and here I reach a point where I have Q. The next thing we can do is add tests within the path. So for instance, here I can go to the right, then I test if the formula I had before is true, then I go to the right again. Okay, so for instance, if I start here, I can go there. There I said this formula is true, then I can go right again, say to this position where I have P. The last thing we can do is have all kinds of Boolean operations on binary relations. So including the complement. So here, I'm saying that I can reach a point where I have P and Q. So basically, this will have to be this position here. And I can reach it by going to the right and also by being in the complement of R. Because from here, I can go to the right there, but these 2 points are in R and not in complement, so it doesn't work. But from here, we are in the complement of R, so that's fine. Okay, so these are a bit random formulas, maybe not so meaningful. So maybe let's finish with one example, which hopefully is a bit more interesting. So take this formula from metric temporal logic. Okay, so this is an until where the second point have to be in the interval described here. Okay, so at position T, the formula holds if I can find a position where I have psi, and which is in between T plus Q and T plus R. Okay, so let's see how we can write this in star-free PDL. So we want to have a position where we have psi in the end. Oh, sorry. And we want to be able to reach it in several ways. So first, we can do plus Q and then go to the right. This means that we are after T plus Q. We can also do plus R and then go to the left. So this means that we are in the right interval. And finally, we want to say that in between the starting point and this point, we have phi everywhere. In other terms, we do not go through a position where not phi holds. So we can take the complement of this expression. Okay, so this is an example of what we can express in star-free PDL. And I mean, generally, we can express all sorts of classical temporal modalities like this. Okay, so that's basically everything you can do. So the examples I gave you are state formulas, so formulas which are evaluated at a given point in the structure. And then you have path formulas. Path formulas are basically anything that can go within the diamond modalities. So you have the atomic relations, then you have the tests, the converse, concatenation, and Boolean operations. So compared to classical PDL, the difference is that we use the operations from star-free regular expressions, so concatenation, union, and complement. In classical PDL, you would have the clean star instead of the complement, so just the regular expression operations. And I mean, there are variants of PDL with or without the converse also. Okay, so this logic is fairly natural in the sense that it combines a feature from many classical logics. So as I said, it's based on propositional dynamic logic. It has the operations from star-free regular expressions. It's also similar to the calculus of relations. So the calculus of relations is a logic based, a logic about relations based on the operation of converse, concatenation, union, and complement. And I mean, it's known that as long as we have those operations, then we capture the full expressive power of the three-variable fragment of first-order logic. Okay, so over any kind of structures, star-free PDL is equivalent to FO3. So this is more of a remark because I'm not interested in arbitrary structures here. I'm interested in interval-preserving one, and I won't need this result, but just to give you an idea of what this logic is in general. Okay, so in fact, I will not use directly this full logic. I will use a fragment of the logic in the translation where I restrict the Boolean operation in this way. So the union is no longer allowed, but we still have the intersection. And the complement is restricted to formulas of this form. So the intuition behind this is that in these fragments, if every atomic relation is interval preserving, then every binary relation you can define is also interval preserving. I mean, it's a bit, there's a bit more than this, but for instance, if you think about the union of two intervals is not an interval, but the intersection of two intervals is an interval. So I mean, it's just different things like that. It's very easy to prove this by induction on the formulas. All right, so the main result is this. So this four logic, so first order logic, the three variable fragment, star-free PDL, and the fragment with any interval preserving relations, they are all equivalent over interval preserving structures. So there are two inclusions which are trivial. I mean, it's just syntactic. This is a restriction of this, and this is a restriction of this. The translation from star-free PDL to FO3 is also pretty simple. So essentially, you can translate state formulas into formulas with one free variable and path formulas into formulas with two free variables. Okay, because the path formula defines a binary relation and the state formula defines a binary one. So it's just a simple induction, really. So for instance, there exists phi looks like this. So we have the formula for pi, and we want to have a y, where we can do pi from x to y and then have pi at y. So that's basically just unfolding the semantics of every construction in the logic. Now, the interesting direction is how do we go from first order logic to star-free PDL, of course. So we proceed by induction still. And okay, so if you have just one free variable in first order logic, you will get a formula with a state formula, and two free variable, you could get a path formula. But here in the induction, we may have formulas with arbitrarily many free variables. So we need to explain what our induction hypothesis is. And yeah, this is it. So any formula, so with arbitrarily many free variables, is equivalent to positive Boolean combinations of path formula from PDL evaluated between two of the three variables of the formula. So this means in particular that any first order formula is equivalent to a finite positive Boolean combination of FO3 formulas, and this is in FO3. So as expected, I guess the atomic cases and disjunction is easy. So the interesting cases are negation and existential quantification. So for negation, the difficulty is that, okay, so if you have the negation of pi is just the complement of pi, it's the definition. But the complement is formula in star-free PDL, but not in these fragments. Remember that we restricted the complements to formulas of this form. But this is not an issue, actually, because the complement of pi is basically just the union of all those formulas plus some additional trivial cases, like if we cannot do, if we are not in the domain of pi or something like that. So yeah, essentially pi is the union of this. And we can prove this just by basically writing up the definition of what it means to be interval preserving. And if pi is interval preserving, then that's it. The other interesting case is existential quantification. So by induction, you have a positive Boolean combination of formulas like this. I mean, you can always push the existential quantifications inside this junction. So you can just assume that we have a formula like this given by the induction hypothesis. And we want to write an equivalent formula without the existential quantification. But this is essentially the same type of formulas as I showed you in the example at the beginning. So if pi I is interval preserving, then this formula says that the intersection of all the intervals, which are the image of xi by pi I, is non-empty. And as we said, this simply means that the pairwise intersections are non-empty. Okay, and to say in PDL that the intersection of the image of pi I and the image of pi j is non-empty, you can just say that, okay, so from xi, I can do pi I, and then I can do pi j backwards, which is this formula. And in the middle line is, again, I mean, it's like before, we need to check that we are in the intersection, in the image of our relation. So we have some additional tests that can forget about it. So yeah, that's just the same proof as the example before. So with this, we have the translation from first order logic into star-free PDL. So yeah, we have the result that we wanted. So that's the main result. So if we have one linear orders and some interval preserving relations, then first order logic is as expressive as star-free PDL or as the three variable fragments FO3. As I mentioned in the beginning, this covers several known results, and it also applies to some other cases. So I have introduced star-free PDL as an intermediate language in the proof, but I believe it's also an interesting logic on its own. As I said, it's really a natural variant of PDL, so it uses classical constructs, and yeah, worth investigating it on its own. So there are several directions where this could be interesting to for possible extensions of this. So as I said, my main motivation was to find sufficient conditions for the k variable property. So I have found some sufficient conditions, but obviously there are many cases which are not covered by these results. For instance, trees and so on. So it would be interesting to find even more general sufficient condition for the k variable property that would cover, yeah, possibly other type of orders or relations of hierarchy and so on. Another thing I would be interested in is, so just like we have many examples of classes of structure where we have the k-variable property, we have many examples of classes of structure where we have an exclusively complete temporal logic. And I think it would be nice if we could also find some sort of general proof that would, cover several known cases. So yeah, that's it basically. So thank you very much for your attention. I would be happy to take any questions.
Thanks a lot, Marie. So now I will unmute everyone so that you can thank Marie. So let me do this just now. So thanks a lot. Okay, so yeah, so do we have any questions? So you can raise your hand. I can see that Dexter raised his hand. So just sorry, let me find Dexter. Okay. Chook spotlight. Dexter, I can unmute yourself and now you can ask your question.
Actually, that wasn't my hand up. That was just applause, the applause icon.
Sorry.
But I do have a question, just a comment. On your further directions, you say generalization to other types of orders, trees. And if I remember correctly, I think in my paper with Neil Immerman, we did do something with trees, but it was so long ago, I don't even remember what it was. So I may have to leave it to you to look up, but there is something in there about trees, as I recall, bounded degree trees, I think. I think we got upper and lower bounds for the number of variables needed to express properties of bounded degree trees.
Okay. So if you have a question, then I think there's a way to wave. So yeah, so please do it. In the meantime, I have a question. So if you restrict yourself to linear orders, is there some hope to get a converse result that interval preserving, so sorry, linear orders with binary relations, is there a hope that interval preserving is actually a characterization of when does FO collapse?
Sorry, no, you can hear me?
Yes,
yeah,
you can answer, yeah.
Yeah, yeah, so actually I wanted to add this in the further direction that I forgot. So yeah, in general, I think it would be very interesting to have necessary condition for the k-variable property. I'm not sure that interval preserving would be sufficient to, would be necessary. But yeah, it would be interesting to have some necessary conditions. The issue is that it's generally very difficult to prove that class of structures doesn't have the k-variable property. So for instance, I mentioned at the beginning that the class of all linearly ordered graphs do not have the k-variable property for any k, but this was open for decades before Rossmann, I think, solved it. So it might be a bit trickier, so it would definitely be interesting to have some sort of converse.
I see, okay. And here is the binary actually, so if you restrict to linear order structures and you can define some sort of interval preserving k-area relation for k more than 2. would it make sense to then get first order collapses to finitely many variables?
So it's not, I mean, you would need to have a definition of what this means to be, and what would be the corresponding notion for hierarchy relations. Yeah, I mean, something that I wanted to look into, and I haven't really had the time yet, but
yeah, okay.
So yeah, I mean, that would be the question, like, can we extend the definition to relations of hierarchy, and then what would that mean?
But are there existing results in that direction of the collapse, for this collapse?
Yeah, so most results I know are about trees, so not so still binary relations. I'm not sure. I mean, not that I don't have any in mind at the moment.
Okay. Do we have further questions? So I'm not exactly sure what's the semantics of the hand that Sławek and Pierre-Yves put. So is this meant to be a question? Maybe let's just ask this directly. Was it a clap as Dexter's? Sławek, do you have a question?
It's Sławek here. It was a clap. It was an applause. I enjoyed it a lot, the talk. No question, just applause.
Okay, thanks. And let me just check Pierre-Yves. Pierre-Yves, was it a question or?
It was also an applause. So
okay, so you all understood the semantics.
But I like the talk very much.
Okay, excellent. So with this, if you don't have, wait, no, okay, so now I got, so Nikolai, where are you? Sorry, I'm not very good with this because I have to go through the list of names to find, yeah, okay. So please, Nikolai, you're spotlighted.
Thank you very much for your talk. I did enjoy it. But question is quite natural. How concise is translation from first order to first order with 3 variables? How concise is this translation?
Yeah, so all the translations.
It seems to me that there should not be any exponential blow up. It seems to me.
So there's, in my translations, there's an exponential, no, a non-elementary blow up.
Non-elementary? Oh,
yeah,
surprising.
basically in all directions. I mean, not from star-free PDL to FO3, but from first order logic to star-free PDL. I have a non-elementary blow up, basically because in the induction I have to always put the formulas in disjunctive normal form and so on. So I have to go from conjunctive normal form to disjunctive normal form, and but I think it's open actually. Like the question of whether first order logic with 3 variables is non-elementary more concise than less concise. I mean, yeah, if first order logic is more non-elementary more concise than FO3. I mean, I looked into it and I think it's, I couldn't find an answer at least, so I think it's still open.
Still open question. Thank you very much. Thank you very much. But by the way, you made your presentation so transparent that I believe that it should not be too complicated. Well, thank you.
Okay, thank you. Dexter, you're back on.
Okay, thanks. I neglected to say last time, thank you very much for a very nice talk. I enjoyed it very much. I was wondering if there is any relationship between the bounded variable property and bounded tree width of models. Suppose you restrict yourself to relational models with bounded tree width. And I'm not sure if you know what that means, but it's a concept where you can overlay on the model a tree, and you can't get from one place to another. There are only finitely many ways you can get from one place to another by long paths. And so there's a concise, a very precise definition of what that means. And it seems like there should be some relationship between that and the bounded variable property. And I'm wondering if you know anything about that or have seen that, anything like that.
So what I can say at least is that it's not necessary. So like for in the example I presented of message sequence charts, I don't know if you remember, so for message passing systems. So these are typically graphs which have unbounded tree widths, and we still have the 3 variable property in that case. So
okay.
Possibly it could help in other cases, but at least it's not necessary.
Okay, thanks very much.
Thank you, Dexter. So we have Dov Gabay. Let me look for you. Excellent. You are, I know I cannot, so your video is not on, so I cannot spotlight you, but you can talk. No, I cannot unmute you. There's something wrong. Dov, can you, do you have audio on? For some reason, it seems I cannot unmute you. Or maybe you want to type your video in the chat. You want to type your question in the chat? Dexter is raising his hand. Go ahead. Sorry.
Nobody can contact you either by chat, or at least I cannot contact you either by chat or by speaking. I can't unmute myself, and my chat is completely disabled.
Yeah, so no, the chat, you should be able to chat with me only, no?
No, I can't chat with anybody. So if you ask a question, like I could maybe make a suggestion, but there's no way to contact you except by waving my arms wildly in my window.
Sorry. Now you should be able to chat with host only. So.
Now I see it. You know, instead of just disabling everybody, maybe just ask people to be nice and just keep themselves muted and only unmute when they care to talk.
I guess that would be a better, So that's actually my first time, so I'm sorry for all the mess up.
That's all right.
Yeah. Dov, no.
Can you hear me now?
Yes.
Yes.
All right. So finally I can say something. At the same time, at the early 80s, I also worked on temporal structures in language. Like English has tenses, you can go past perfect, future perfect, all that. Russian is full of aspects. Swahili, you can say something, he coughed repeatedly for the next to the last time. These are all temporal structures in language. And I was asked by linguists, is it possible that some languages are more expressive temporally than other languages? Okay, that's the question I had to check mathematically, given that I was working on the mathematics of expressive power. Mm-hmm. And my answer to that relates to the to this lecture, actually, because all languages can do the following, and this is really all languages. First this, and then that, and then that, and then that, and all of this in the future, or all of that in the past. So you give a sequence, you push it to the future, or you push it to the past, and this complex again, you push to the future, story within a story within a story, and you shift it around. Yeah. But this is exactly the binary relation, in fact, one-to-one relation, where you take an interval and the relation just pushes it to the right or pushes it to the left. And that gives you 3 variables, and 3 variables is full expressive power, and we've done. You see? Every language in the world can tell you a story and say, yeah, that was last year. Or, yeah?
Yeah, that's an
so
interesting.
that's my comment.
Thanks.
I don't remember where I published it, but the linguists were very happy.
Yeah, that's an interesting way to look at it. Thank you.
Thanks a lot. So I don't see any more hands raised. So I'll stop now the Q&A session and I'll stop the recording.